It's morning here in Winnipeg, and apparently later in the day in the Ukraine. My talk is I am Jim Peters at the University of Manitoba, and my talk is on homotopic nerve complexes with free group presentations. And the talk itself is dedicated to two mathematicians, a topologist, Somni Nampoli, and another mathematician, Saroja Banavar, who incidentally is my mother-in-law. And I want to thank the organizers for their invitation to give this talk. I'm very happy to be with you. Okay, this is an overview of the topics in my talk, starting with elementary one cycles that map to homotopic cycles, and revert back to an idea in 1935 by Alexandrov and Hopf and Alexandrov. Uh, what Alexandrov introduced was the notion of a nerve, a structure, and I extend that to what I call a homotopic nerve. And then Rothman, 1984, I believe, he introduced what he called a free group presentation of a structure. And I give three examples of free group presentations based on the structures I present. And two of them are new and introduced in this talk. And the third part of the talk is on application of the ideas in the talk in terms of Betty numbers. Here's an example of something that is similar to what you would find in Hatcher in his 2002 algebraic topology book that you can download from Cornell. This structure on the left is an example of a what is known as a one cycle. And the one cycle is a collection of vertices that are path connected, and there are no inverts, no vertexes. And the interior of the one cycle is non-empty. And that maps to a homotopic cycle in which the edges or one cells in the conventional one cycle are replaced by homotopic maps that construct, in each case, an edge mapped from the unit interval to points either on the endpoints, the vertices, or the interior points. Okay, here's a definition of a one cycle. I've explained that already, so I won't belabor it. I'm working in all cases in a CW space, a topological space introduced by Whitehead in 1949, which is actually an elaboration of the topological space introduced by Alexandrov and Hopf in 1935 in their topology book, written in German and not in translation. They enunciated the conditions for a CW space without mentioning Hausdorff, but mentioning the two conditions for a CW space, namely containment and intersection, which I'm sure you are familiar with. Here is the definition for a homotopic cycle, which I pictured earlier. And what we have with a homotopic cycle is a collection of homotopic maps ranging from, with indices from 0 to n minus 1 mod n, where n is the total number of vertices in the cycle. And each homotopic map is a mapping, a continuous mapping from the unit interval to the CW space K. And the square bracket n is a shorthand, very convenient shorthand for mod n. And I'll do all my work on the indices for each homotopic map. So H sub 0 would be considered the first vertex in a homotopic cycle. where we have vertex V0 in the CW space, this is equal to the homotopic map n minus 1 mod n of 1. Okay, so when we write that as V minus 1, n minus 1 mod n in the same space. The inverse, this is the interesting part, the inverse is gotten by working with the indices rather than the way Hatcher does. Hatcher works with the argument of a homotopic map. This is Hatcher's introduction, his way of viewing inverse maps, inverse homotopic maps. I view them in terms of the indices. I do this, these indices are on the, however, if we want to generalize this, then the indices would be over the interval, the unit interval 0 to 1. And then I introduce, this is important later when we talk about homotopic free group presentations of these structures. I introduce this binary operation on k cross k to k, and I want to explain that this actually ends up being a movement from one vertex to another. But we have then, if you have plus v prime or v and v prime are vertices in one of these cycles, then we know that if we've designated one of these vertexes as a generator, then every other vertex can be written as a linear, a multiple, an intermultiple of that generator element. So I can write it like this. And then notice that I can replace G by, because G is actually H sub 0 of 0, I can write that as K H sub 0 of 0 plus K prime H sub 0 of 0. And I'm going to take these coefficients and drop them down to the index for that homotopic mapping. And that gives me a new vertex in the CW space. So here's a definition of a nerve complex introduced by Alexandrov in 1935 in his beautiful little book you can download from the internet, and elaborated by Alexander Berhoff in their topology book. And namely that if you have a nerve complex, it is a collection of non-empty cell complexes with non-void intersection. So we get the theorem, which is easy to prove. A pair of, from the definition, a pair of one cycles with common vertex in a CW space is in fact a nerve complex. And here's an example to show you what I mean. We have this is a pair of one cycles with a common vertex shown in green. And here we have some elementary results. One of them published recently by me, that every vertex in a triangulation of the vertices in a CW space is in fact the nucleus. It's the common vertex of an Alexander-Popp nerve complex. And then the theorem is that a CW space containing n triangulated vertices contain n Alexandrov nerve complexes. Okay, now a homotopic nerve is an extension of this idea of a nerve complex on edges, as for example on one cycle edges, and that carries over to replacing the edges by homotopic maps. So we have a homotopic nerve. It's a collection of homotopic cycles with non-void intersection. And then we have the theorem that every collection of homotopic cycles with a common vertex is in fact, in a CW space, is in fact, by definition, a homotopic nerve. Easy to prove and not necessary for us to belabor. Okay, here we have an example. This is a homotopic nerve where I have a common vertex for this pair of homotopic cycles. And by definition, that common vertex is in fact a homotopic nerve. Okay, now I want to just go back a minute and look at the idea of a triangle, I'm going to introduce the notion of a homotopic triangle. Given a set V of three vertexes in a CW space, a sequence of homotopic maps over those three vertexes constructs what's known as a homotopic triangle. And every collection of these homotopic triangles with non-empty intersection is, in fact, another Alexandrov nerve. Here's an example. I take the centroid of a homotopic cycle. I triangulate on the vertexes and that centroid to get this rather beautiful structure, triangulated structure. Okay, then I do something that Alexandrov does in his little book, and that is to let B be a collection of various solutions on the triangles of a homotopic cycle, a triangulated homotopic cycle, and the edges between each pair of barycentric, adjacent barycentres helps those edges on those barycentres define a barycentric one cycle. And that leads to, by the same method as used before, it constructs a barycentric homotopic cycle. Here's an example. I have, these are nested homotopic cycles, and I have the inner homotopic cycle is on the barycentres of the triangulated, the outer homotopic cycle is triangulated on that centroid to give me this structure, a barycentric homotopic cycle. Okay, then now we go to the presentation, which is really the heart of what I wanted to get at, and that's the notion of finite group presentation. So we start with a structure, a set of vertices, including a generator and other vertexes on a cycle, either conventional in a CW space, like a one cycle, or a homotopic cycle. And then I have this set of relations where each vertex is written as a linear combination of the generators. And I map that combination X cross triangle to a group. And it's a free group. And that free group is called a presentation of that pair. Now, here's an example. This is just a lemma that was introduced by me in 2020 and by my co-author, Tainver Gilly. And here we have every one cycle in a CW space K has a free group presentation. And this is just a matter of rewriting what the definition by Rothman in terms of the vertexes that are in the one cycle in a CW space K. The relations are in terms of each vertex written as a linear combination of generators. If it's a one cycle, there'll only be one generator. And then we can define the continuous map from 2 to the K, which is the set of all subcomplexes in the CW space crossed with the triangle to that set of collection of subcomplexes in the CW space. And we define that mapping in terms of this set taken from the arguments. I have a set of vertexes equal to the linear combination of the generating elements that are in the triangle. And the vertexes themselves are in a cycle. And I have a basis, which contains the generating elements, and the coefficients K sub I are in the integers. And that gives me then my group, and this is Rothman's notation, G, which is just it's a combination of the set of basis elements, the generators, and the operation plus, which I explained earlier. Then we're going to carry this over by a rewrite of what I just did, because this is a proof sketch for this lemma. Now, if you take that, the proof sketch, you can rewrite it and get this result, that every homotopic cycle in a CW space has, in fact, a free group presentation. Here, the rewrite is in terms of the generators being homotopic maps like this one. Okay, then we have, let's see, sorry, the next one is that I can now introduce homotopic nerves. Homotopic nerves is a collection of homotopic cycles with a non-void intersection. And we have the easy to prove theorem that every homotopic nerve in a CW space is a free group presentation. And we get that easily by rewriting the proof sketch that I gave just a minute ago. And here's an example. Now this is now notice here, there's one change in the earlier drawing, and that's that I've introduced a homotopic mapping from a vertex on the inner homotopic cycle to a vertex in the outer homotopic cycle, and I call that a bridge homotopy, a homotopic edge. Okay, then we get this, that a homotopic nerve is in a CW space a collection of homotopic cycles with non-void intersection. Every homotopic nerve type of nerve has a free group presentation. Easy to prove again using which is a proof which is symmetric, what I gave earlier. Here's the proof sketch. Sorry, here we have the definition of a homotopic bridge, which I won't repeat. I gave you already. And here's the definition of a homotopic vortex. It's a collection of nested homotopic one cycles with non-void intersection. Or is this vortex has at least one homotopic bridge between each pair of non-intersecting cycle vertexes in the vortex. And again, I can get out of that free group presentation of that homotopic vortex. My computer is slowing down. Here's a drawing of what I just said. This is a drawing of a homotopic vortex nerve where the homotopic cycles have an intersection, a common vertex, namely H4 of 0. Okay, and then I have this, I think I'm repeating myself, just a minute. This is all we need. We have then every homotopic vortex nerve, which is what this is in fact, just a second, is in fact, if you have a structure like I just showed, it has a free group presentation, and that's symmetric with the proof given earlier. And then we go over Benny numbers. And this is our application. I think I have time to show you. A Benny number in this case is a count of the number of generators in a free group. This is Monkrest from Monkrest 1984. And I'm going to show you now what this looks like if I apply this. This will give you something restful for your eyes. This is an implementation of this idea. And here, I hope everybody can see that. Can you see this? Is it visible? Okay, well, anyway, I hope it is visible. Then what we want to do is look at this again, and then we can go back and forth and compare the Benny numbers of each of these vortexes. And that concludes my talk.